Hello everyone and welcome to the workshop Data Science. In this workshop you will learn how to build your own machine learning models with a range of Oracle technology. My name is Jeroen Kloosterman and I'm a product strategy manager for Oracle. I'm presenting this workshop together with my colleagues Frederik Bergstrand, Lyudmil Pelov and Hans Wiemann. And also special thanks for the team that has helped behind the scenes. If you're interested in Oracle products such as the Data Science Service, machine learning in a database, Oracle Analytics and also Graph, then you're in the right place. I hope you're ready to work because we'll be mixing presentations with exercises that you'll be able to do in your own cloud environment. As you probably know, data science and machine learning also comes with some theory that you need to know, and we'll be covering this along the way. So we'll talk about things such as supervised and unsupervised learning, linear regression, neural networks, etc. This also means that there are no real prerequisites for this workshop. If you still remember your statistics classes and if you already know some Python and SQL, that would help, but again, it's not an absolute necessity. The agenda. In the first presentation, I will cover some data science basics and a high-level Oracle portfolio overview. In the video for Lab 1, we'll cover the theory behind data exploration, and you'll do an exercise to predict house prices with the Data Science Service. The theory for Lab 2 covers neural networks, and it's followed by an exercise to recognize handwritten characters, again using the Data Science Service. Lab 3 covers a business user angle to data science with Oracle Analytics Cloud, and you'll be doing an exercise to automate credit scoring. Lab 4 covers Oracle in-database machine learning, and here you're going to train a model in database and later operationalize it in an Apex application. And Lab 5 lastly covers Graph. It turns out that graph databases have an interesting relationship with machine learning, and you'll learn about that in this lab. So let's get started. To start, we should first cover some essential theory behind data science. Some people may already be familiar with this, but I just want to make sure that we're all on the same level before we go to the labs. Now, before we talk about data science, we have to talk about machine learning first, because machine learning will be the actual tool that you'll use to make predictions or recommendations. And I'll come back in a second on how machine learning fits into data science. So what is machine learning? Well, I find this a very complete definition. Machine learning is the scientific study of algorithms and statistical models that computer systems use to perform a specific task without using explicit instructions, relying on patterns and inference instead. So we're trying to let the computer do a task. In other words, we're trying to automate something. And you'll notice here, without explicit instructions. So the whole point of machine learning is that you can let software reach a certain objective without explicitly programming it on how to do that. And the key to this is in the word patterns. Machine learning relies on finding patterns in data that we present to it. In other words, it will learn how to do the task from the data. Pretty similar to how you and I learn something, right? You could say that our experience is our data that we learn from. And the keyword inference, that means that once you know the patterns, you can apply it to new data. So we bring what we've learned into practice and we actually do something with it. If that sounds vague, let's go through some examples. Of course, all of you have heard about self-driving cars and Siri, so let me go through some very different examples. And all of these fit more in a business context. One of my favorite examples is in sales and marketing. Imagine that you have a product that you want to sell and you want to create a campaign for it. The challenge here is that you don't want to send out campaign material to all of your customers. No, you only want to select those customers that you actually think you will sell it to. The way it typically worked in marketing is that people would use their instinct to decide on what the best audience is. And in this traditional way, these marketeers would write some complex rules to select the audience that they think is the best one. But that was pretty hard to do because you have to rely on experience and maybe you had to do some manual analysis. So instead, if you use machine learning, those rules are basically written for you. Imagine that you have some data of customers that already bought that product and some customers that didn't buy. Then you can use that data for learning. So we feed into a training algorithm all the data that we think might be relevant to the issue. Think of customer data, think of demographic data, historic purchasing, similar customers, etc. And then the algorithm looks for the patterns that drive purchasing and stores that knowledge in what we call a model. Once we have that model, we can feed the data of any customer into it to predict whether this customer will be interested in buying the product. If we have enough quality example data, then our predictions can be better than what can be achieved through human instinct. And because we're taking advantage of the knowledge that was previously locked away, that was previously hidden in that data. Another example, did you know that in the medical world, machine learning can be used to make diagnosis of medical images? The input data for the model training process in this case are many images that have first been manually labeled by doctors. For example, having pneumonia or being healthy. And some hospitals have experimented with this and found out they actually reached higher accuracy diagnosis than with a human approach. Let's take one more example. Machine learning can also be used for fraud detection. And fraud detection can be anything from credit card fraud and attempts to hide money laundering to insurance and social benefits fraud. And again, here you could do something similar. If you know of some transactions that are definitely fraudulent, then machine learning can find the patterns in the data. But there are also other ways in which machine learning can help here. There's a class of algorithms that help you identify fraud by simply finding those transactions that look different than the rest. And we call that anomaly detection. And then there's yet another technique for this fraud detection that focuses on the network of transactions that sometimes exist in a web of bank accounts and all the activity between them. We'll come to that technique later when we discuss graph databases and its relationship with machine learning. So what is that model that we're talking about? Well, the easiest way to think about it is as a mathematical function. Imagine that we're trying to predict the price that a house will sell for when we just know its size. You know now that machine learning learns from existing data. So let's plot the historical data that we have on house sales. And on the vertical axis here you see the house price, and on the horizontal axis the house size. Training a model is all about fitting a formula that best represents the pattern in the data. And in this case, the linear regression algorithm, which by the way we're going to use in our first lab, the linear regression algorithm will try to fit a linear function or a straight line to the data. The equation for this line in this case is basically our model. So if you remember well from high school, the formula for a linear function is fx is ax plus b, with the result fx being the target value, the house price in this case, and x being our input feature, the house size. Training using the linear regression algorithm is all about finding best values for a and b. So let's pretend we have obtained those values for a and b. So we've basically trained our very simple model. We can now go to the prediction phase. And let's say we have a house that's 200 square meters and we want to know its expected sales price. Now our function now tells us that the house will be around 400,000. So you see how a model generalizes from example data and is then able to predict values for new data. Now, of course, this is an oversimplified example. In reality, you'll use models with many more input features. And in some cases, the model's internal representation is indeed such a mathematical formula as we see here. But there are also algorithms where that's not the case. For example, decision trees or neural networks, they have a very different way of capturing the patterns in the data. But still, conceptually, you can think of any model as a function. Machine learning algorithms fall into roughly 3 categories, and I think it's important that you have a grasp of these. First of all, there's supervised learning. What makes this unique is that here we have labeled historical data. Labeled means that our example data also holds the value of the thing that we try to predict. So for example, Ask yourself now, in the example for predicting house prices, is that a supervised learning problem? And yes, of course it is, because we have the house prices of that historical data. So we can train a model on a known correct target value. You'll hear people talk about regression and classification. In regression, we're predicting a continuous number, a value. So indeed, our house price prediction is an example of that. On the other hand, sometimes we want to predict a class or a category. For example, we want to predict whether a customer will churn, yes or no. This is an example of classification. So in the case of classification, we are also creating a function, but in this case, the function will find the borderline between the classes and the line that best separates the different classes from each other. Now you'll gain some experience on classification in the lab on in-database machine learning. Unsupervised learning is different because there we don't have a label. We don't have desired expected output data. So we cannot follow a training approach as we did with supervised learning. Instead, what we do is just give the algorithm a set of input data, and we basically ask it to find the hidden patterns in this data. The most common example of this is clustering. For example, take a list of customers and separate them into two groups. In this case, it's up to the algorithm to find which customers are most alike, looking at all of their attributes. You can also use this technique to find anomalies in data. For example, for that fraud detection that I mentioned earlier. Reinforcement learning is entirely different. Here, think for example about how you would teach a dog a trick. With a dog, you would basically wait until it does something that's similar to what you want, and then you give it a reward. And the idea is that over time, the dog will adapt its neural network or its function to reach the goal that you want. We can use this same mechanism to teach a robot, for example, to pick up something on a factory line. Initially, this robot will have a model that lets it move rather randomly. But if it happens to get a bit closer to the goal that we've set, it will get a kind of reward by the system. And when that happens, the machine learning model of the robot will change its weights. And in the end, we will have a robot that reaches its goal without us having to tell it how to do that. Now we know what machine learning is, let's see how it fits into the other important concepts. You have to see artificial intelligence as the overarching concept that includes the machine learning capabilities of today, but also things that are not necessarily possible yet. That's why I'm always very careful in using the term AI, because a so-called general AI, where one algorithm or agent would be able to handle any problem, that simply doesn't exist yet. What we do have today is what's called narrow AI, and that's essentially machine learning. And this is what you're going to learn about. In machine learning, we train models that can perform one particular task. So I can train a model to find fraudulent transactions, but I cannot use that same model for a self-driving car. Within machine learning, there's a subfield called deep learning, and this is all about using neural networks, which are based on how the biological brain works. If these networks have many layers, we call it deep learning. And these type of networks have demonstrated the ability to solve many problems that we couldn't solve before with the traditional machine learning algorithms. Generally speaking, problems that involve image or audio or video are often addressed with deep learning. And for example, think about image and voice recognition. And data science, and now I'm talking about the concept of data science and not the Oracle service with the same name. Data science is the field, the study, the process of using machine learning and deep learning and implementing actual cases. So there's a process behind making machine learning work for us, and there's a lot more to data science than just building a model, as we're going to see in just a minute. So what are the languages that you should know to do machine learning today? Now here's an overview of the languages that data scientists mostly work with. And at the top of it is Python and the popular machine learning libraries that have been developed for it. You might have heard of scikit-learn, of TensorFlow and of Keras, and these are very well-known machine learning libraries for Python. There's an enormous community of end users for these libraries, and the development in this open source community also goes very quick. R is still popular as well, but it's giving away terrain to Python, and SQL is also a skill that many data scientists have. In business situations, the source data that they work with often comes from databases, and SQL can also be used to perform data exploration and data preparation as well, as we'll see later on. Now you may think, okay, let me take some data and just train a model on it. Well, it's not exactly that easy. There's a process behind data science, and building a model is just one of the steps, as I mentioned. Because before you can build your model, there are various steps around data access and getting the data ready for training. Machine learning is all about data, so the success of any initiative will largely depend on the availability of the right data sources. So we will want to first identify which data sources in an enterprise are relevant, and then those data sources are consolidated in one single place for our data scientists to access it and to experiment with it. A big part of the data scientist's job is to explore and to massage the data in such a way that it's optimized to do model training. And let's say we've done that and we've trained and evaluated and selected our model as well. Then comes maybe the most important of all, bringing a model into production. Machine learning almost always leads to predictions or recommendations that are actionable. So our goal must always be to productionize our models, to make the models part of applications or part of business processes. For example, if your model predicts which customers are going to churn, then why not use that knowledge in a CRM application or automatically send out a mail merge? So another takeaway here is that an important part of data science is bringing those models into production and also managing these models once they are in production, continuously evaluating their performance. Building machine learning is not a waterfall approach. It's more about experimenting and adapting continuously. In advance, you do not know exactly which data configuration will give the best results. You may not know in advance which algorithm is the best. In fact, you don't know whether your result will be good enough at all to solve the business problem. So often you'll have to hop back in this process to change the data, to change the algorithm, etc. It's not like you're building an application where you're pretty sure that you'll be able to complete the task. So that's really what I mean with experimentation. And as mentioned, in this workshop, you'll experience what it is to work on most of the steps in this life cycle. To conclude all of this, let me highlight some of the typical difficulties that companies run into with their data science initiatives. We see a lot of initiatives starting out small, where data scientists start building models on their local machines, on their laptops. And although that may work okay for a while, people quickly run into some limits. First of all, it's difficult to locate that so important data that they need for training. It's also not uncommon that people have copies of sensitive data on local systems that are impossible to govern. And it's not easy to cooperate with fellow data scientists from these isolated local environments. We also see that data scientists have enormous problems in taking the models that they've created and integrating them into the business, in an application, for example. So imagine, there you are as a data scientist doing groundbreaking work, but nobody is able to see the results of it. At this point, I think it helps to make the comparison with application development, because application development is a very mature discipline where developers are used to collaboration and a streamlined DevOps process. And the field of data science is much younger, and you notice that data scientists are not yet used to working in a more organized model. It's Oracle's goal to change this and create a streamlined process. Collaboration between data scientists and other stakeholders, and easy access to all the resources that are needed in the process, be it databases, data lakes, compute power, etc.